Welcome to another VCE physics coaching video. We've looked so far at gravitational force fields and electric force fields. So the third one we're going to look at is magnetic force fields. And so certain objects, it was discovered a long time ago, attract anything made of anything made of metals, in particular iron, not any metal. So had to be made of iron, or cobalt is another what we call magnetic material. And these objects also interacted with what was later discovered to be the magnetic field of the Earth. And so the certain end of an object would point to geographic north. And so we call that the North Pole. But in fact, it was pointing to the S pole of the Earth if we considered the Earth to have a magnetic field. But can get a bit complicated talking about the magnetic field of the Earth, and it doesn't come up too much really in the examination. So we'll look at, in particular, the field lines for a magnet. So there's a magnetic force field is dipolar. It has an N pole and an S pole, whereas gravity is monopolar. Okay, and an electric force field can be monopolar or dipolar. So we might be asked to draw some field lines. So we'll draw some here now. Didn't mean it to be a square. Let's see if we can make that into a bit of a loop. So a question might ask us to do certain number of field lines. Field lines go from N to S, or north to south. We tend to use the terms N to S for fields. So to not be confused with a geographic north and south of the Earth. So if we're asked to do four field lines, you can see that there. All right, so you might be asked to draw a combination of fields. So I'll just do a very simplified diagram for this one. N to S is the direction of field lines. So that's an N and an S, that's unlike poles facing each other. They will attract. You can see the field lines joining together. But if the fields are like poles, again, we might just be asked to draw four field lines, and they'll repel against each other. So if they were S and S there, then the field lines would be going into the poles, not out, as is shown here. All right, so that's the field lines around permanent magnets. I'm probably going to go quite quickly through some of these. So you've got a textbook more than likely that will have some more better quality published diagrams, but just really want to model what it's like to draw field lines in real time, because that's what you'll be asked to do perhaps in an examination. So it was discovered by a Danish physicist, Hans Ørsted, that electric current has a magnetic field around it. It was discovered by accident, I think, when he switched on an electric current and a compass needle near the wire moved and lined up with the field lines. So for a current carrying conductor, we've got on the left here, there's a certain rule for defining the direction of a magnetic field. And we call it the right-hand grip rule. So imagine we've got our thumb going up the screen, or up the page, let's say, and your fingers of your right hand are curling around the back of that wire and then back around the front. So if you were looking from the top down, that would be anti-clockwise, I think, if we're looking from the top down. And then if you've got a series of coils, it's a little bit more complicated, but there's a rule called the right-hand coil rule. You can either apply the right-hand grip rule to each individual coil, or there's a special rule I quite like called the right-hand coil rule. Imagine you've got your right hand and your fingers are going up the back of these coils and down, curling up the back and then down the front of the coils. That means your thumb would be pointing to the right and the field lines would go something like this. With your thumb pointing to the right, that means that would be an N pole and that would be an S pole. I've just got a bit of a diagram there. You can see there's another rule we could use. It's just a bit of a learning aid, that if you looked from the left, the current would be going clockwise, but I've written the word S in there with the arrows on the end of the S, matching the clockwise nature of the current. And if I'm looking from the right end, then the same works with N. So that's just another little trick. Right, so that's, again, a very quick walkthrough of what field lines directions are for current carrying conductors, either a straight carrying conductor or a number of coils in the form of a solenoid, is what we would call this. All right, so if we've got a current carrying conductor, such as this one, in the presence of an external magnetic field, that means we've got two magnetic fields interacting with each other. So that means we'll get a force happening. So there's a formula we need to know for the size of the force, and it's F equals NBIL. And I'll go through what each of the quantities are there via an example. So L stands for the length of the wire in the field. I stands for the current in amps, and B is the magnetic field strength in Tesla. And N is the number of wires that would be bundled together. If it's more than one, then we've got to write that number. So we'll do this example. Let's work out the force in newtons on that current carrying conductor. So F equals NBIL. So if it's 5 wires bundled together, that's 5. I might say, let's call it 5 times B, that's 500 milliteslas. So that's 500 times 10 to the minus 3 Tesla times the current, 2.0 amp, times the length. If it's 10 centimeters of wire in the presence of the field, then that would be 0.1 meters. We've got to use meters as a standard unit. And if we put all that through the calculator, you can check my working out, but I understand that comes out to 0.50 newtons. All right, so now because force is a vector, we've got to have a rule for the direction of the field. And that's called the right-hand palm rule, not as distinct from the right-hand grip rule. So the way it works is we take our right hand and make our thumb go in the direction of the current, which in this case is up the screen or up the page. All right, so it's a little bit hard to convey this in a 10-minute video. Probably need to do some exercises. It could take a good several hours to do all of this. But this is, if anything, this is a summary of everything you'll need to know. And even more complex problems come back to all of these basics. So because there's a possible of 6 directions, in, out, left, right, and up, down, we've got to have some conventions for directions. So into the page means is given by a series of crosses, and out is by a series of dots. So in this case, we've got a field going into the page. So my fingers, again, my thumb is going up the page. I've got my fingers going into the page at the moment, or into the screen. And then my palm, if I keep everything at 90 degrees to each other, the palm is facing to the left. And so the force on this is going to the left. So that's the right-hand palm rule. It's clearly going to take just a bit of practice, but once you get it, you'll definitely get it. So moving on, that's for, in this case here, that's the direction of the force and the size of the force on a current carrying conductor. That's charges constrained by a wire. But what if we've got free charges? What if we've got a flow of charge, either positive, like protons, in this case moving to the right, or it might be electrons with negative charge moving either to the right or the left. So they also experience a force. The relevant formula here is F for the force equals QVB, where Q is the charge in coulombs, V is the speed in meters per second, and B is the field strength in Tesla. So again, what if we've got a proton, let's say, moving at 2 × 10⁶ meters per second. So Q, you need to know that the electronic charge is 1.6 × 10⁻19 coulomb times the speed of 2 × 10⁶ meters per second times the field strength of 500 × 10⁻³ So again, check my working out. I've put this through the calculator a little earlier and I get 1.6 × 10⁻13 newtons, which is a small force for one proton. But then again, we've got to have a direction for that force. And we use the right-hand palm rule again, which is defined as positive. So we use the thumb going to the right here for positive charges. If it's an electron, we've either got to use the left hand or flip the thumb to the other way, to the left. But I'm going to make my thumb go to the right and my fingers are going into the page or the screen. That means the force, that my palm is facing up the screen. Now, any force which is perpendicular to the charge and constant in size will make a circular path, okay, of a certain radius. The stronger the force, the tighter the radius, or smaller the radius, and so forth. All right, so just very quickly, when looking at magnetic forces, we've got to be able to draw field lines around a permanent magnet, also combinations of magnets, field lines around current carrying conductors. So again, just to be able to draw the field lines, and the relevant formulas is F equals MBIL for the size of a force on a current carrying conductor. And for the direction of the force, we use the right-hand palm rule, either for a current carrying conductor or for a moving charge, a free charge. And here's a formula once again, just for the size of the force on a free moving charge. So thanks for watching another VC physics coaching video. I hope you can use this to solve all your exercises related to magnetic force fields.